right, so last time we talked about acid-base titrations when it was a strong acid and a strong base. So for a strong acid and a strong base, because when they react, the reaction goes completely to the products, we were dealing with the limiting reactant. So before the equivalence point, you would have, for example, if you were titrating a strong acid with a strong base, so you were adding the base to the acid and measuring how many milliliters of base you've added. Before the equivalence point, the base, you have less of that than the acid, so that's the limiting reactant. So we just did the before and after tables. So we would go to completion, see what the pH was of our leftover acid. At the equivalence point for a strong acid, strong base, you have equal moles of the acid and the base, assuming 1-to-1 stoichiometry, so you just had a pH of 7. After the equivalence point, if you continue adding base and overshoot the end point, then you end up with more base than acid. So you would be finding, after you use the limiting reactants, now your acid, whatever your leftover base is, find the pH of that. So those were the acid-base titrations we did last time. And we just introduced the idea of, well, what if you have a strong base titrating instead of a strong acid, a weak acid? So we already talked about at the equivalence point you have equal moles because I'm dealing with a weak acid, a strong base. The base is stronger, therefore our pH would be in what range? Acidic, basic, or neutral? If I have a weak acid but a strong base, basic. So we expect a basic equivalence point, and sure enough, here's with sodium hydroxide and I believe this is acetic acid. Our equivalence point right here is at 8.5. Marker out. About 8.5-ish, which is slightly basic. And we were about to talk about how we calculate that. So with this, now we have a strong base titrating a weak acid. In this case, we have acetic acid plus sodium hydroxide. The products are sodium acetate and water. Now, in the case of the strong acid, strong base we did before, the acid-base neutralization produced a salt in the water, exactly the same thing here. But in that case, it produced sodium chloride. So in the last acid-base titration, we weren't concerned about how sodium chloride would affect the pH because it's a neutral salt. As we learned 2 lectures ago, though, is sodium acetate a neutral salt? Yes, sometimes the sodium is written in the front. It's all right. Is that a neutral salt, an acidic salt, or a basic salt? Back to chapter 16. Can sodium affect the pH? No, it's the conjugate of a strong base, so it's not affecting the pH. Can acetate ion affect the pH? Yes. I have a weak acid over here, acetic acid, which makes the acetate ion its what? Good, strong conjugate base. So can it affect the pH? Yes. But at this point, we have to worry about not just what products are, but also still have to worry about what point of the titration we are. Just like with the strong acid, strong base, before the equivalence point, the base was our limiting reactant. Still, if we're before the equivalence point, the base is still our limiting reactant here, which means sodium hydroxide, that's our limiting reactant, that will go down to 0, and what I'm left with is leftover acetic acid and leftover sodium acetate. So I have a weak acid and a salt containing its conjugate base. What do we call solutions that contain a weak acid and a salt containing its conjugate base? We just learned about that last class. What was the special kind of solutions that we made from weak acids and salts containing their conjugates? Good, a buffer solution. So these two together make a buffer solution.
So why did you cross out the sodium?
Hydroxide? We're talking about if we are before the equivalence point. So that would be our limiting reactant. We would have a buffer solution. So the way that we determine the pH during this titration depends if we're before the equivalence point, at the equivalence point, or after the equivalence point. So first we're going to talk about before the equivalence point, we will have a buffer solution. So how do you find the pH of a buffer solution? You can do it with an ice table and the common ion effect, but what was the faster way that we did it last time? Good, the Henderson-Hasselbalch equation, which says the pH of a buffer solution is equal to the pKa plus the log of the conjugate base over the acid. That was how we found the pH of a buffer solution. So before the equivalence point, we are going to be a buffer solution. So let's talk about, let's see here. Prior to the addition of the base, we've got, say, did they give an amount here? Oh, this is just talking about before you've added any base. You've just got the weak acid to find the pH of the weak acid is just an ice table, so that's just chapter 16. Once we start adding the base, though, before the equivalence point, then you've got the hydroxide ion turning that acetic acid into the acetate ion. So let's say, for example, did they give an amount? Okay, 10 milliliters of base. So we have 10 milliliters of base containing 1.55 millimoles of acetic acid and 1 millimole of the acetate ion. Let's go back to where those numbers came from, because I don't know why, for some reason, it didn't show up on the slides. But if we're following along, we're on page 793. So we have a 0.1 molar acetic acid, and we have 0.1 molar sodium hydroxide, and we're going to add, for this one, 10 milliliters of base to, did they give an amount, starting amount of sodium? 25 milliliters, yeah. 25 milliliters of 0.1 molar acetic acid. And first we're going to add 10 milliliters of 0.1 molar sodium hydroxide. So because this first reaction goes one way, we're going to do a before and after table, and we're going to do it instead of in molarity, we're going to do it in moles or millimoles. Millimoles will probably be easier here. So again, molarity is millimoles over milliliter. So molarity times milliliter equals millimoles. So how many millimoles do we have of acetic acid initially? We have 25 milliliters of 0.1 molar. .5, good. 2.5 millimoles. And how many millimoles do we have of the hydroxide ion from the sodium hydroxide? 1. So it's easy to see here because our stoichiometry is 1 to 1, which one is the limiting reactant. So which one's the limiting reactant? Acetic acid or hydroxide? Hydroxide. So hydroxide is going to go to 0 millimoles, which means it's going to change by how much? Minus 1 millimole, which means the acetic acid is also going to decrease by the same amount because the stoichiometry is 1 millimole. And we will be left with how many millimoles? Over here on the product side, what's going to happen? We can ignore water, it's a liquid. But what about the acetate ion? Good, we're going to add 1 millimole. So now we have 1.5 millimoles of acetic acid and 1 millimole of the acetate ion. So that is what kind of a solution? We just said it. A buffer, good. So we have the weak acid and its conjugate base. So we're going to find its pH using the Henderson-Hasselbalch equation. So here is our equation for the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the base of the acid. pKa, again, is the negative log of the Ka. So for acetic acid, last time the Ka of acetic acid was 1.8 times 10 to the negative fifth. So the pKa, the negative log of that, we found to be 4.74 for acetic acid. Plus the log of the base over the acid. So my conjugate base is the acetate, so that's 1 millimole, and my conjugate acid, or my weak acid, is 1.5 millimoles. Now, in the Henderson-Hasselbalch equation, what goes inside that log, that ratio, it can be a molarity, or it can be in millimoles. Because this is the same solution, and molarity is divided by volume. It doesn't matter if you convert it back to molarity or not, since they would both be divided by the same volume, it would not change the ratio. So to make our math easier, we're just going to leave it in millimoles when we find the ratio. There. So we're just going to leave it as 1 millimole over 1.5 millimoles, and that gives us a pH of 4.56 for that point in the titration. So for a strong base, weak acid titration before the equivalence point, you have a buffer. Do a before and after table to figure out how many millimoles you have left over of your weak acid and how many millimoles you have of your conjugate base, and plug it into the Henderson-Hasselbalch equation to find the pH of that solution. So that's the pH before the equivalence point. So what do you think we're going to find the pH next of? At the equivalence point. So the equivalence points where you have equal moles of acid and base, assuming 1-to-1 stoichiometry. If it's not 1-to-1, at least equal moles of hydrogen ion from the acid and hydroxide ion from the base. So at the equivalence point. Now, in the case of at the equivalence point, let's find, we have an equation? No, they give us equation. At the equivalence point, let's go back to this one and just erase this so we have space. I'll ink on the slide. So again, we were starting with 25 milliliters of our 0.1 molar acetic acid, which is 2.5 millimoles. So at the equivalence point, how many milliliters of hydroxide would we have added? To get equal millimoles, how many milliliters of hydroxide would we need to add? 25 as well. Good, because they're both 0.1 molar milliliters, which would give us 2.5 millimoles. Now, which one is the limiting reactant, or are they both going to go down to 0? Good, they both go down to 0, which means they both decrease by 2.5, 2.5. Over here on this side, we're going to increase by 2.5, so we have 2.5 millimoles, and then we ignore water. So at the equivalence point, what kind of a solution do we have? It's the only thing left there. Sheet 0. What's the only thing left that could possibly affect the pH? The strong conjugate base right here. This is what's going to be left that could possibly affect the pH. Now, that is the strong conjugate base because it is the conjugate base of a weak acid. Yes, there's still also sodium floating around here, but it's going to be a spectator ion, so we're pretty much ignoring him. But technically, it's part of that conjugate base, making this an ionic compound that is soluble. What do we call ionic compounds that are soluble? That we found the pH of back in the end of chapter 6. What solutions? They will be electrolytes, but one of the things we were finding the pH of last chapter, in chapter 16, finding the pH of what solutions? Chapter 16, we found the pH of strong acids, strong bases, weak bases, and what's? Salts. Good. This is a salt solution. So again, the sodium ion we're ignoring. What really is going to affect the pH is the acetate ion. So how did we find the pH of a salt solution back in chapter 16? What did we do with this thing? We've got 2.5 millimoles of this acetate ion. How can the acetate ion affect the pH? What is it going to do with water? COO minus. If this is a conjugate base, that means in water, what is it going to do? Make what? It's going to make hydroxide. Good. It's going to turn water into hydroxide, which is going to leave it as what? What is it going to turn into? The acetate ion. Back to acetic acid. Good. Is this reaction going to go one way or both ways? Both ways. This is a weak reaction, so we're going to go both ways. So if the reaction is going to go both ways, and to find the pH, what do we really need the concentration of? Concentration of what is what we plug into a pH equation, or POH? The what? Hydronium. Hydroxide. Well, hydroxide. So we would need to know what is the concentration of that. So how do we find the concentration of that thing? How do we find the concentration to put into the negative log equation? We don't know its concentration. We only know about the acetate ion. Ice table. Good. Ice table. So we did an ice table. So when we do an ice table, are these going to be in millimoles or molarity? Water again. Molarity. Do we have molarity of our acetate ion? Do we have molarity of the acetate ion? No, you're not sure. What do we know about the acetate ion? How much do we have of it?
2.5 millimoles.
Good, we have 2.5 millimoles. That's not a molarity, but can we use that to find molarity? Yes, molarity is millimoles over what? Milliliters. So how many milliliters do we have? At this point in the titration, we started with 25 milliliters. We've added 25 milliliters, assuming volumes are additive. We have how many milliliters? 50 milliliters. Good. .05 molar acetate ion. All right, so what's going to go in the change row for our ice table? Negative x. So on the equilibrium, we're going to have 0.05 minus x. What's going to go over here? Plus x, x, and x. X looked weird. All right. So how do we solve for x? Good, equilibrium constant. So we need to know what is the K of this. Is this going to be a Ka or Kb? Are we acting as an acid or base here? Base. So this is going to be a Kb. We need to know what is the Kb of the acetate ion. X out of this so I have more space. Keep that. Slide. So how do we find the Kb for the acetate ion? Because you're not going to find that in a table. We don't know what the Kb of acetate is. We know that the Ka of acetic acid is 1.8 times 10 to the negative fifth. We got that from the table of weak acids back in chapter 16. Can we use that to find the Kb of the acetate ion? Yes. What's the relationship between Ka and Kb? Good. The product is equal to what? Good. 10 to the negative 14th. So Ka times Kb for conjugates, multiply them together, you get Kw, which is 1 times 10 to the negative 14th, which means that Kb, what is that? I'm not sure if it's Kb. Kb is going to be equal to 1 times 10 to the negative 14th divided by the K of acetic acid, 1.88 times 10 to the negative fifth. So what does that work out to? Good. 5.56 times 10 to the negative 10. So now we can plug that into our results from the ICE table, which is that we have products of X and X on the top and a reactant of 0.05 minus X on the bottom. Bottom. How do we solve for X? Good. Probably a good assumption to say X is small because our K is so tiny. So if we assume X is small, we can ignore this minus X. If we ignore him, then we can do what to both sides? Square root of both sides. So square root of 5.56 times 10 to the negative 10 is 2.36 times 10 to the negative fifth is equal to square root of x squared, just x, over square root of 0.05, 0.224. 36 to the negative fifth. I'm getting 5.3 times 10 to the negative 6. Is equal to my x. So if that's x, going back to our ice table, that is hydroxide. So that is my concentration of hydroxide ion. So now how do I find pH? Negative log of that will give me POH. So negative log of that is 5.28. Nah. Good. 14 minus that to make pH. pH is equal to 14 minus 5.28, which is 8.72. Now, we are at the equivalence point of a weak acid being titrated with a strong base. So what did we say we expected the pH to be? Neutral, slightly acidic, or slightly basic? Slightly basic. Is that number slightly basic? Yes, it is. It's slightly higher than 7, so that is definitely a slightly basic. So our answer makes sense. Always go back and look back at the big picture. It can be easy with these titrations to get bogged down in the little details and miss the big picture. Always step back whenever you get to an answer and look at the big picture and say, does this answer make sense? If not, something went wrong somewhere. If yes, it does make sense, that feels good. Feels like I did something right. It also helps if it agrees with what the textbook says. And it does. So again, before the equivalence point, we had a buffer. So we found the concentration of the leftover weak acid and resulting conjugate base and did the Henderson-Hasselbalch. At the equivalence point, we had a salt solution, so we solved it using an ice table. So what do you think the last part of the titration we're going to do is? After the equivalence point. So if we overshoot the equivalence point and end up with more base than acid. So let's see. Let's do, if we've added, let's do 35. Yeah, sure, we'll do 35 milliliters. Let's see. We'll do, I'll open another slide. All right. So I'm going to write once again that we have acetic acid, CH3COOH, being titrated with sodium hydroxide. So we're really just worried about the hydroxide. And the products are the acetate ion and water. All right. So again, we were starting with 25 milliliters of 0.10 molar acetic acid. At 25 milliliters of the 0.1 molar hydroxide ion, we were at the equivalence point. So somebody give me a volume that is greater than 25, but not like, up to 40, just slightly greater. 30. So let's add 30 milliliters of hydroxide ion. 0.1 molar of the hydroxide ion, and that should overshoot nicely. Now again, we're going to start with the before and after table rather than an ice table. Because this reaction goes one way, we do not need to start with an ice table. So the initial final tables, instead of being in molarity like an ice table, because this is just stoichiometry, they're in moles or millimoles. So again, millimoles, molarity times milliliters. So we started with 2.5 millimoles of the acetic acid. And in this case, how many millimoles will we have of the hydroxide? 3.0. Now, which one's the limiting reactant? It goes down to 0. The acid goes down to 0, which means it decreases by 2.5 millimoles. If it decreased by 2.5, how much is the hydroxide going to decrease by? Same. Which means we're going to be left with what? 0.5 millimoles. Now over here, my water, we're also technically adding 2.5 millimoles and leaving left with 2.5 millimoles of the acetate ion. So here's the question, which one is going to affect the pH? Both of them technically are going to affect the pH, but I have hydroxide, which is a strong base, and then I have the acetate ion, which is a strong conjugate base. Which one is stronger, a strong base or a strong conjugate base? Hydroxide. Hydroxide is much, much, much stronger. But when I keep on saying the strong conjugate base is a relative term. It is strong compared to other conjugates. It's still not even on par with most weak bases. It's very, very weak compared to a strong base that would have given us hydroxide like this. Sodium hydroxide gave us hydroxide. Because of that, although both of them are going to push the pH up, make it basic, the one that's going to have a significantly greater effect is going to be that hydroxide. For that reason, we can ignore the effect of the acetate ion and just focus on the effect of our strong base. So moving forward, that's what we're going to use to find the pH. Does everybody understand why we're ignoring the effect of the acetate ion? It's so weak that by comparison it's not going to change things that much, at least not measurably. So we have 0.5 millimoles of hydroxide. How do we find pH from that? pOH is the negative log of the concentration of hydroxide, right? Is that a concentration, 0.5 millimoles? No, but can we use it to find concentration? Yes, molarity is millimoles over milliliters. So we have 0.5 millimoles divided by how many milliliters? Good, 55 milliliters. Because we had 25 plus 30, assuming volumes are additive, we're up to 55 milliliters. So 0.0091 molar. So negative log of that is our POH. Negative log of that is 2.04. So what is our pH here? Good, 11.96, which is pretty far in the basic end, which is what we expect. Past the equivalence point, we're just adding strong base to a neutral solution, which is going to turn it to a strong base. So again, weak acid, strong base. Before the equivalence point, we have a buffer solution, use Henderson-Hasselbalch. At the equivalence point, we have a salt, use an ice table. Past the equivalence point, we're going to have excess base, so just find the pOH of that excess base. Makes sense? Ready to try one? All right. And hey, look, we did it right. We had 30 milliliters of hydroxide, 11.96. Let's try this again. Calculate the pH in the titration of 50 milliliters of 0.120 molar acetic acid by 0.240 molar sodium hydroxide at these three places after the addition of 10 milliliters of the base, 25 milliliters of the base, and 35 milliliters of the base. Want to guess what those three, A, B, and C, are going to represent as far as what point of the titration you are? Good, before, at, and after the equivalence points. Probably good guess here. All right. So in this case, we do not have equal concentrations of acid and base, but that's okay. When we do these tables and find millimoles, it's still just whatever our molarity is times our milliliters at that point. So let's focus on part A, which is probably going to be before the equivalence point first. So again, here's our equation for our weak acid acetic acid reacting with the hydroxide to make water and our acetate ion. Again, we're ignoring the sodium ion as a spectator ion, so we're just focusing on those things that can affect the pH. So part A says we've added 10 milliliters to the base. So first of all, what happened to the screen there? I don't know. Let's find millimoles of acetic acid. I don't know why that's acting weird. How do we figure out millimoles of acetic acid? Millimoles are equal to what? Good, the milliliters times the molarity. So 50 milliliters times 0.120 molar is how many millimoles? 6, good. 6 millimoles of acetic acid. So in part A, how many millimoles do we have of the base? We've added 10 milliliters and it's 0.24 molar. What's 10 times 0.24? 2.4. Good. Shouldn't even need a calculator for that. Ignoring water and starting with no acetate ion. So which one is the limiting reactant, the hydroxide or the acetic acid? The the hydroxide. So that's going to go down to 0. So minus 2.4, minus 2.4. So what's 6 minus 2.4? .6, good. And over here, we're going to increase by 2.4 and have 2.4 millimoles of the acetate ion. So what kind of solution do we have here? And how are we going to find its pH? It's a buffer. Good. We have acetic acid, which is a weak acid, and we have the acetate ion, which is its conjugate base. So this is a buffer solution. So how do we find the pH of a buffer solution?
Our percentage is before the equivalent point that we buffer.
As long as it's a weak acid, strong base. Yes. What's our equation for the pH of a buffer? pH is equal to? Good. 4.74, which is the pKa of acetic acid, plus the log of the base over the acid. So here's our base. The thing that keeps on flashing for some weird reason is our acid. And can we leave it as millimoles, or do we need to convert those to molarity? You can keep it as millimoles. It's not going to affect the ratio. So the base goes on top, so the 2.4 goes on top, and the 3.6 goes on the bottom. What's the pH for part A? Well, we've got two significant figures, so we're going to have 3 significant figures in the final answer, 4.56. Any questions about part A before we move on to part B? All right. Now in B, now we've added 25 milliliters of the base. So that means what is now our concentration, or our millimoles of hydroxide? Again, millimoles is the molarity times the volume. So 0.24 times 25 gives us what? 6. Hey, look at that. Are we at the equivalence point? Yes, which means these both are going to go down to 0. And we're going to be left with 6 millimoles of the acetate ion. How do we find the pH of that? 6 millimoles of acetate ion. Ice table. So to go into an ice table, we need concentration. So we need to take these 6 millimoles and turn them into molarity. Molarity is millimoles divided by milliliters. So how many milliliters do we have in part B? 75. Good. We started with 50, and so far we've added 25, so 75 milliliters. So we have a concentration of 0.08 molar. All right, so if we were to now do an ice table, we would now have the acetate ion reacting with what? Water. Good. To make our hydroxide and our acetic acid. All right. And we're starting with the concentration of 0.08 molar minus X. 0 plus X, 0 plus X. So K is going to be equal to X squared over 0.08 minus X. What's this K going to be equal to? KB. So KB we found from the Ka of acetic acid. Go back to that real quick. Ka of acetic acid is 1.8 times 10 to the negative fifth. So 1 times 10 to the negative 14th divided by that Ka gives us a Kb of the acetate ion of 5.56 times 10 to the negative 10. So we'll just go ahead and use that instead of calculating it again. To avoid quadratic, what's probably a safe assumption here? X is very small, so we're going to ignore that guy. Take the square root of both sides. And we're left with X over 0.283 is equal to 2.36 times 10 to the negative fifth. So X will be equal to 6.67 times 10 to the negative 6. Once we've found X, how do we get that into a pH? Negative log, because X is hydroxide, so negative log will give us POH. Some space here. POH is 5.18, which means the pH is 14 minus that, or 8.82. For part B, the answer is 8.82. Does that answer make sense? Again, let's take a step back and look at the big picture. We have a weak acid being titrated with a strong base, so at the equivalence point, we expect our pH to be what? Acidic, basic, or neutral? Basic. Is that a basic pH? Yes, so our answer makes sense. It's basic, but not too basic. As you might be catching on, depending on where you are in the titration will affect the amount of work it takes to find the pH. At the equivalence point, when you have a salt and you have to do the ice table, that's probably the most work there is. But at this point, you've done these ice tables so much, shouldn't take that long to fill one out, right? Any questions before we move on to part C? So if here at 25 milliliters we were at the equivalence point, at 35 milliliters we would definitely be past the equivalence point. So let's go back to our original table, erase this, and see what we're up to. So part C, where we have 35 milliliters of base, how many millimoles is that of base? Good, 8.4 millimoles. So now our acetic acid is our limiting reagent. That's going to go down to 0. And we're going to be left with 2.4 millimoles of base and 6 millimoles of its conjugate base. Which one's really going to have a bigger effect on the pH, though, the hydroxide or the acetate ion? Hydroxide is going to have a bigger effect, and that is the OH. So we can find pOH from its concentration. So let's first find its concentration. Molarity is equal to millimoles over milliliters. How many milliliters do we have in part C? 85. Good. 50 plus 35 is 85 milliliters for a concentration of 0.028 molar. Let's give us some space over here. We're not worried about acetate ion anyway. So if we take the negative log of that, that will give us the pOH. So pOH is the negative log of 0.028, so that is 1.55, which means what is the pH? Good, 12.45. We're adding more base, so we are expecting this to get more and more basic as we go on, and yep, it makes sense. We are getting more and more basic as it goes on. All right, so we've done strong acid, strong base, weak acid, strong base. What do you think we're going to do next? Strong acid, weak base. So let's flip the script on this. Any questions about this? Everybody got to copy down before we move on? Again, this practice problem was on page 795. There we go. All right. Now, a strong acid, weak base titration. At the equivalence point, what will we expect the pH to be? Acidic, basic, or neutral if we have a strong acid and a weak base? Acidic, yes. So here's an example of a titration curve made from 0.1 molar hydrochloric acid being titrated into, so the acid now is what's in the burette, being titrated into 0.1 molar of ammonia, NH3, which is a weak base. So at the equivalence point right here, we have a pH of, looks like it's a little bit less than 5.5, which is slightly acidic, so that makes sense. We start off with a pH that is basic because we're starting off with ammonia. And then after the equivalence point, when we have all that extra acid, we have a very acidic pH. So looking at this reaction, hydrochloric acid is our strong acid. Ammonia is our weak base. The product of this is ammonium chloride, which is a salt. It's an ionic compound that is water soluble. This is a salt. Is that a neutral salt, an acidic salt, or a basic salt, though? How can we figure that one out? We've got two parts of the salt. We have the ammonium part and we have the chloride part. Can chloride affect the pH? No. Hydrochloric acid is a strong acid, which makes chloride its conjugate base a what base? Strong acids have what conjugate bases? Weak conjugate bases. So the chloride ion is not going to be able to affect the pH. Can ammonium NH4 affect the pH? Yes. If ammonia is a weak base, then ammonium NH4 plus is a what? Good. Strong conjugate acid. Which makes this a what salt? Acidic, basic, or neutral salt? Acidic. Good, because it contains a strong conjugate acid, which is why at the equivalence point we have a slightly acidic pH, because we have that acidic salt left over. So ammonium acts as a acid because when it reacts with water, you have an equilibrium that produces ammonia and hydronium. So it acts as an acid. It donates a proton to the water, H2O, making water H2O into H3O. Let's try this out. Before the equivalence point, we're going to end up with leftover weak base and also some of that conjugate acid that we have formed here. So let's consider the titration of 25 milliliters of 0.10 molar ammonia with 0.10 molar HCl. Now, we're going to end up with, they jumped right into the ice table, didn't they? Oh, they calculated the initial pH using an ice table. You completely ignored the HCl. I don't know why they started off by asking this question and then find the pH of before the titration has started. So before the titration started, we just have the weak base. So we do an ice table for a weak base, solve for X, find the pOH and then the pH from that. So 11.11 should be before the titration even starts. So we're right here, 11.11. I don't know why would they ask that question, and then even in the textbook, they ask the question and then don't actually show you how it's solved.
So for the equivalence point for this kind of problem, that's what we would do.
No, you're not at the equivalence point. That's before the titration started.
Before
Before the titration has started, it's just finding the pH of the weak base. All right, let's just jump into the problem. I think the problem will make more sense than what they had there. So let's calculate pH at the equivalence point when 25 milliliters of 0.1 molar ammonia is treated with 1 molar of acetic acid. So here's our reaction. Hydronium is from the HCl. So HCl is making the hydronium. Ammonia reacts with hydronium to make ammonium and H2O. Now, we have, at the equivalence point, equal moles of the acid and the base. So let's, because we're not told what volume are being added of the acid, let's go ahead and figure out what volume of acid we need to add to make the equivalence point. So we have 25 milliliters of 0.1 mole ammonia. If our HCl is the same concentration, how many milliliters of HCl will we need to add to reach the equivalence point? 25 milliliters as well. So at the equivalence point, we have added 25 milliliters of HCl, which means our total volume, Cl, what did that, our total volume right now is what? 50 milliliters, good. So our total volume is 50 milliliters, and at the equivalence point there, we started with 2.5 millimoles of the ammonium ion and 2.5 millimoles of the ammonia and a hydronium. I'm mixing up my words here. 0 plus 2.5. So at the equivalence point, what are we left with that could affect the pH? NH4. NH4 can affect the pH because it is a strong conjugate acid. So basically what we're left with is a salt. So how do we find the pH of a salt solution? Ice table. So we're going to do an ice table with ammonium. So ammonium in our ice table, we found the concentration of it using millimoles divided by milliliters. So 2.5 millimoles divided by our 50 milliliters equals what concentration? Good, 0.05. That's what goes into our ice table. 0.050 molar ammonium. Now we do our ice table, reacts with water. It's acting as an acid, so it turns into hydronium and turns the ammonium into ammonia. Minus x plus x plus x. So K will be equal to the products x times x, or x squared, over the reactants, 0.050 minus x. How do we find out what K is to plug in here? Is this a Ka or a Kb? Ka, good. It's acting as an acid. This is a Ka. So we need to find what is the Ka of ammonium. So how do we find the K of a conjugate? Because you're not going to find that in a table. How do we do it in the last problem? We found the K of the acetate ion. We found it by doing what? Good. Ka times Kb equals Kw, or Ka in this case would be Kw divided by Kb. So Kw is 1 times 10 to the negative 14. Kb, what is the Kb that goes in the bottom here? It's what? Have to look it up. We have to find out what is the Kb of ammonia, NH3. So back in chapter 16, we had a table of weak bases and their Kbs. Now, here's the fun part. Kb for ammonia is 1.8 times 10 to the negative fifth. Sounds familiar, doesn't it? Which is what? Same as the Ka for acetic acid. So you'll end up with 5.56 times 10 to the negative 10. Careful though, that number on the bottom, I've seen students just assume it's always 1.8 times 10 to the negative fifth. It is for acetic acid, it is for ammonia. If I gave you another weak acid or another weak base, though, make sure you're looking up that number. That's where that number came from. It just happens to coincidentally be the same number as in the last problem, even though it's a different problem now. All right, so set that equal to 5.56 times 10 to the negative 10. Now to solve for x to make our lives easier, let's assume x is small, so we're going to ignore that guy, take a square root of both sides. This part's starting to feel very familiar. Finding x to be 5.23 times 10 to the negative 6. So if that is x, how do we find pH from that? Good. A negative log of that, will that give us pH or POH? pH, good. Because that is hydronium, so negative log of that will be pH. I'm getting 5.28. As always, take a step back, look at the big picture. We titrated a weak base with a strong acid, so we expect the pH at the equivalence point to be acidic, basic, or neutral. Acidic. Did we get an acidic pH? Yes, that is slightly acidic. Not too acidic, just slightly acidic, so it makes sense. All right. Any questions about that before we take a step back from the math for a little bit? I think we're done with the math, right? All right, so in the last couple of minutes of class, we're going to talk a little bit about indicator solutions, which we touched on briefly in lab last week, talking about acid-base indicators. So what was the indicator we used in the lab last week? Phenolphthalein. Good. Phenolphthalein is what color in acidic solution? In acidic solution. Clear. But in basic solution, it turns what? Pink. So right when the titration switched at the equivalence point, we were titrating a weak acid with a strong base. So at the equivalence point, is our pH acidic or basic? Slightly basic, which means our color with phenolphthalein should be slightly pink. So that's why we picked phenolphthalein, is because we were titrating a weak acid with a strong base, so at the equivalence point we expected a basic pH. Would that be, phenolphthalein be a good indicator to use if I was doing this last titration, if I was doing this one here, 25, or our hydrochloric acid with ammonia? Would phenolphthalein be a good indicator for this titration? Yes or no? No, because at the equivalence point, my pH is 5.28. Phenolphthalein would still be clear at 5.28 because it doesn't turn pink until it's in a basic solution. So picking the correct indicator solution requires you to know what pH you expect to have at your equivalence point. So how do indicators work? They work by being pushed in one direction or another through an equilibrium reaction through Le Chatelier's principle by either an acid or a base. So in this case, I have some conjugate or I have some indicator. It has hydrogen ion in the acidic solution. In the base solution, it's just the negative ion. This is an equilibrium reaction, so if I add a little bit of acid, I'm going to push it in this direction. If I add a little bit of base, I'm going to push it forward. Depending on what color you have of this indicator could be a different color in acidic solution, could be one color. For the case of phenolphthalein, is colorless. And in a basic solution, this would be a different color. In the case of phenolphthalein, that's where the pink color turns up. The end point of the titration is the point at which you see a color change. So this was one of the questions on your lab last week. What's the difference between an equivalence point and the end point? The equivalence point is where you had equal moles of acid and base, assuming 1-to-1 stoichiometry. If it's not 1-to-1, at least equal moles of your hydrogen ion from your acid and your hydroxide ion from your base. The end point is where you see a color change. You want to pick an acid-base indicator that has an end point close to what you expect the pH of your equivalence point to be. So in the case of phenolphthalein, phenolphthalein's color change starts occurring about 8.3-ish is where it starts turning that pink color. So we wanted to pick it because we know at the equivalence point of a weak acid with a strong base, we have a pH in that range. Whereas if we wanted to do an indicator for the last problem, the ammonia with the hydrochloric acid, which ended up having a pH of 5.28, a better indicator would probably be methyl red. Methyl red changes color in a range of 4.2 to 6.3. So methyl red would have been a better indicator for the ammonia being titrated with HCl. So, and here is a table. This table is on page 800 of common pH indicators and the range that they change colors in. So a common question from this would just be, what color indicators would you use for the following acid-base titrations? And you're just going to look for which from this table have pHs in those range. Since we're out of time today, you can do that one on your own. This practice problem here is on page 800, right underneath the table. All right, so on Thursday we will finish, or on Wednesday we will finish up this chapter, and then on Thursday we will have a lab and have your homework for chapter 17 due.